So let me go over a few things first. First, you have a homework due Friday, and the review session was yesterday, which is tomorrow. Friday's tomorrow. However, there's a problem on one of them, number 5, for some reason, is there's an extra 2 in the answer or something. The answer is like, it's just off, right, by a factor of 2. So, you got it right? Well, you're off by a factor of 2. So, you don't have to do number 5, although you should do it. I mean, it's only by a factor of 2. It's not like a gigantic deal. But nonetheless, if you don't do it, you'll get credit for it, right? But if you want to do it, you can do it either way. You should know how to do it, for like when the test comes around. The rest of them are fine, though. So you have a quiz this weekend, regardless of what's going on with the poll, which I'll talk about in a minute. But you have a quiz basically on what homework that's due Friday is on, which is conservation of energy. It was a huge chunk of it. Okay, so test 2 grades are almost done. It takes a while because you have a lot of students. But they should be up sometime tomorrow. But we have this pumpkin drop thing tomorrow at 10 a.m. And I can't really do anything until the majority of that is over with. So after that, but then we have to leave school by 2 because they're kicking us out at 2 too. So sometime tomorrow I'll have the grades up, and when I put them up, I'll obviously put what you got on test 2, but I'll also update all your averages, your homework average, your quiz average, your test average, your overall average. Yeah.
Will that be with the 2 that you dropped?
No, I'll probably drop 1 up into this point, but I will put that in there, like dropping 1 so far, because there's 2 of each that are dropped, right? Okay, so this brings us to this thing with the test, right? Which could be next week, or might not be next week. So yes, there's more than one student. It wasn't just one student. I don't do it for one student, but more than one student made a compelling argument to move the test up a class. So I don't really want to do that, but see what the class says, right? So I made that poll. And then, after I made the poll, I got a bunch of emails that, I don't want the test the week after because I have a test the week after. All right, well, everyone has tests the week or the week before. It can't be perfect. It's just the way tests go. So whatever the poll says is what we get, right? And it would be, I'll announce that tomorrow too. Now, for the people that have tests the week after and complaining that you don't want the test moved up, there's no homework assigned this week. It'll be assigned some other. I'll explain that in a second, right? So this week there's no homework, right? So, and I'm going to post the equation sheets already posted. I'll post the topics, the PowerPoint topics that I do this weekend too. So what I would do if you have a test the week after, if it's the week after, it could be next Thursday too. I'll let you know tomorrow. Saying hypothetically if it's the week after, I would study as if it's Thursday, right? And then just look over the material, the following week if it's truly the Tuesday after that. Because you won't have any homework this weekend, so you can study for it this weekend and start studying for it next week, and treat it as having the test next Thursday. Next Friday, I'm going to assign a homework. So that's the bad thing with the homework. If it's the Tuesday is that you have a homework due that week of the test. But I don't think it's a huge deal because most people don't start the homework until after the review session anyhow, and the review session is the day after the test. And no matter what happens, if you have the test on Thursday or the Tuesday after, the review session next week is going to be just a review for the test. If you have the test on Thursday, then also in Tuesday in class we'll review for the test. And if we have it on Tuesday, then on Thursday we'll review for the test, right? So you'll get an in-class review and then review session review next week for the test, right? So I'll let you know after it closes on Friday, immediately after, so you know whether, it's a really, regardless, I think you should try to start studying for the test, no matter what day it is, right, over the weekend. All right, so are there any questions on that? I probably won't do that again, by the way. It's a bad idea. Yeah?
It's in a month from now, but week of Thanksgiving, are we going to have homework?
No. So that's the last thing I want to say about test 3. Test 4 is 2 weeks after that, and that's fixed. However, the material on test 4 isn't too bad, and you'll see how test 4 goes. So I don't want to get into logistics of test 4. We haven't even had test 3 yet. but just trust me, it's not too bad. So you will, the class technically ends before Thanksgiving, kind of, sort of ends before Thanksgiving. So there's nothing after Thanksgiving, all right?
So thank you.
Are there any other questions on that stuff? Okay, so it is a little bit weird though, and especially if the test is the week after, because I'm going to do test 4 material now. And then most of next week is test 4 material, except for a part of a class for review. But that's the way it's going to go. All right, so the next thing that we're going to talk about on test 4, which basically starts with the momentum. The momentum is the first main topic on test 4, which is the last test. Is, well, the next thing we're going to talk about is how things rotate. Because so far we only talked about basically things just sliding along surfaces, sliding down inclines. But if you have a ball or something, or a tire, they roll and they rotate. So you have to figure out how things work when things rotate. So we have to talk about how things rotate, basically, rotational dynamics. So that's the next thing we're going to talk about. I haven't posted these PowerPoints yet because you have test 3 coming up, but I'll post them, I guess. It's not a big deal. You can ignore them if you want to ignore them before test 3. But the next thing we're going to talk about is rotational motion energy. Now, the good thing about this stuff is in the beginning, it's got to be a little bit weird, and you have to think about things a little bit. But in the end, it's actually pretty straightforward. It's very related to, very much similar to what you did on test 1, actually, this stuff here. So you'll see how this works in a minute. In the beginning, it's a little confusing, but then in the end, it's much easier to understand once you see the whole picture of how things work. Okay, so, oh, I forgot to bring it in the other class, but I think I brought it. I think it's on it. Okay, so I didn't bring this in the other class, but I brought it in this class. So suppose you have something that's rotating, like this DVD, right? So it can rotate it can spin about its middle, right? That's typically how things spin. They don't have to spin about the middle, but suppose it's spinning about the middle, right? So it's rotating, and it's spinning, and it's spinning. We'll talk about how it spins in a minute, right? So what you can do is you can focus on like a point on the edge of the DVD, right? So as this thing is spinning like this, if you watch my finger, it'll move, right? From here to here after some time, if I wait some time. So what I can do is I can relate something that we already talked about, which is average speed, to something new that which we haven't talked about yet, which is basically average angular speed, which is how fast something is spinning on average, right? So how do we do this? Okay, so basically, if you focus on the edge and it's spinning about the center, and you wait, some amount of time. I got to do this too because of people watch. This point will move from here to here, right? Like my finger will move from here to here, right? So when it does this, it moves some distance. What distance does it move? It moves along the edge of the DVD or the circle, right? Whatever distance that is. Well, that's called an arc length, right? So basically, you can figure out using geometry what the arc length is that it moves. You can relate it to the radius and everything, which I'll talk about in a minute. But the point is, if you know how far it goes and the time it takes to go that distance, you can calculate the average speed of the thing, right? That's just what we did in test 1. So the average speed is just the distance that it goes, which is how far it goes from here to here, which in this case here is from here to here, divided by the time it takes to travel that distance, which is the time you waited for. That's the average speed. But you can also relate it to new things, right? So basically, you can take the distance and relate it to the radius and the angle, the angle that's swept out, what we call swept out. So what's the angle swept out? If you draw a line from the center of the disk to where it starts and then a line from the center of the disk to where it ends, it sweeps out some angle, right? If this thing, this is the angle that it sweeps out, right? That's what we call delta theta. So by geometry, the arc length here, the distance that goes from here to here, is equal to the radius times the angle that's swept out, right? It's r times delta theta. It's just a geometry thing. So one way to understand this is if you go all the way around the circle, come back to where you start, how far have you gone? What's the distance that you travel if you go all the way around and come back to the same point? The circumference, right? You travel a circumference. What's the equation for circumference? Anyone know? 2 pi r, right? So what's the angle that you go if you go all the way around?
360 degrees.
Right, but the other way to say that is 2 pi radians, right? So if you take 2 pi, multiply it times r, you get the circumference, but that's if you go all the way around, the angle is 2 pi. If you go partially around, then it's d times delta theta times r is d, right? Okay, that's the general equation. So you stick this in for average speed. Average speed is distance over time, but d is r divided r times delta theta, so you get this equation here. And then if you factor out the r, you get delta theta over delta t times r is the average speed. Now, delta theta over delta t is something new in rotational motion. It's the first thing that we see that's new. This is called the average angular speed, right? So what it tells you is basically, on average, how fast something is spinning, right? Because if delta theta, if you wait some time, right, and the delta theta that it sweeps out is bigger than if you wait some other, the same amount of time, but delta theta is less, it means that the average angular speed is bigger, right? Which means it's spinning faster. It sweeps out more angle in the same amount of time. So basically, this thing here, called the average angular speed, is just defined to be delta theta over delta t. And by the way, this is a Greek symbol called omega. It looks like a W, but it's omega. And sometimes I say omega instead of the angular speed, but it's the same thing, right? Omega and angular speed are the same thing. So this is the average angular speed. It's just defined to be how much angle is swept out divided by the time it takes to sweep it out. But it's a measure of how fast it's spinning, basically, on average. This is the first new thing. The units for omega is units of angle per time, except we don't use degrees when we talk about rotational stuff. We use radians, right? So it's not degrees per second. It's typically radians per second, right? So you're going to get a little bit used to radians. It's not too bad. We'll see examples of it in a bit. But it's radians per second. So when you see something, how fast something is spinning, it's typically measured in radians per second. But something else you can do with this is you can relate how fast this dot is moving, or my finger is moving, to the average speed, I should say, the average speed of how fast this dot's moving, to the average angular speed. It's just given by this equation here. It's just average speed is equal to r times the average angular speed, right? So that's the first thing that we talk about when we talk about rotational stuff. So let me just say something. If you go back to what we did on test 1, when we first did physics, right? What do? We did 1D kinematics. So what do we do when we did 1D kinematics? Anyone remember the progression? We did average speed. Well, we did distance and displacement. Then we did average speed. Then we did velocity, right? Average velocity. Then we did instantaneous velocity and all that stuff, right? So this is where we're starting here. We're talking about the average angular speed, right? For this, for things that are spinning. Now we're going to talk about instantaneous cases. Okay, so that's the next slide here. Okay, so this is where it gets a little bit weird, but then it gets clearer on the next couple of slides, right? So this slide's a little bit weird, but it makes sense after you see the next couple of slides. So let me try to explain this slide first. So what I just talked about is the average angular speed, right? This is kind of like the average speed, right, when we did the 1D kinematics. Then we talked about instantaneous velocities. Remember, we did like VF is equal to VI plus AT. Remember, you can find the velocity at any time. Remember, the instantaneous speed is the magnitude of the instantaneous velocity, remember? So something at some moment in time is going like 20 meters per second in the positive x direction. The speed is 20 meters per second, right? It's just going in the positive x direction. That's the instantaneous speed. So you can do the same thing here. You can do an analog between the rotation stuff that we're talking about now and the stuff that we did in the first test. What I mean by that is there's this average angular speed, but there's also an instantaneous angular speed, right? So what's the instantaneous angular speed? It's basically how fast the thing is spinning at some time, right? So this thing could be changing speed all the time. Maybe spinning faster and slower. So if you figure out how fast it's going at one particular moment in time, that's the instantaneous speed, right? Now, when you did instantaneous angular speed is what I meant to say. When you did instantaneous speed, once again, it was the magnitude of the instantaneous velocity, correct? Remember? We did this on test 1? Okay. So there's something else you can talk about for angular speed. It's called the angular velocity, right? And the magnitude of the angular speed, the magnitude of the angular velocity is the angular speed, right, at any moment of time. So this is what I'm talking about here. This is the angular speed is equal to r omega, but there's also an instantaneous angular velocity associated with the angular speed. And you might say, well, how do you describe how things move when they spin? Well, it's pretty straightforward. When things spin, they only spin two different ways. They spin counterclockwise or they spin clockwise. So that's how you would sort of say it. You would say it's spinning at 10 radians per second counterclockwise or 10 radians per second clockwise. I don't know which one, but either way. And later on in the slides, I'll show you that we have notation for that. Basically, it's positive if it's spinning counterclockwise. So basically, you can think about something sort of like something moving in the positive x direction. And if it's spinning clockwise, it's something like it's negative, which basically is sort of like something moving in the negative x direction, right? It's just counterclockwise or clockwise, right? So you don't want to write counterclockwise and clockwise all the time. So we say counterclockwise is positive, clockwise is negative, right? That's it. Okay, so so what you can do is take this average equation here, right? This is the average speed is equal to r times the average angular speed, and turn it into an instantaneous equation. So this is the instantaneous speed, right? How fast something's moving is equal to r times how fast something's spinning at that moment in time. Okay, now what is this v? Okay, so suppose you have this disk, right? Suppose you have this disk, right? It's spinning around, and I put my finger on it, and my finger spins with the disk, right? So as the disk is spinning, my finger is spinning around with the disk, right? And if I want to figure out how fast my finger is moving, this is what I'm talking about. I use this equation here. So this is my finger, right? It's spinning around the disk like this, right? If I want to figure out how fast it's moving at this point here, all I do is I take how fast the disk is spinning, which is omega, and I multiply it times r, where r is the distance from the point that you're looking at to the point that it's spinning about. So if it's spinning about the center, you measure the distance from the point that you're looking at in the center, and you multiply that by how fast it's spinning, and that gives you how fast that thing is moving, right? That's something that now we can calculate if we know how fast something is spinning. Not only this, we can call this something. This is like the v that we talked about the whole semester. It's just the v that we talked about the whole semester. However, in the context of rotational motion, we call it something, we label it a little bit differently, which is called the tangential velocity. Now, why is it tangential velocity? It's because if you watch this point spin around with the disk, it's got to spin in a circle, right? It's got to go like this. So at this moment of time, it's moving in this direction here, which is tangent to the circle. So this is how fast it's moving in a direction that's tangent to the circle. That's why we call it tangential velocity. But it's just sort of like the velocity we're talking about the whole semester, right? No different, really, but we call it tangential velocity in the context of this stuff here. All right, so this slide's a little bit weird, but it makes more sense in the next few slides. All right, does everyone have that so far? The general idea how you can relate v to r? Oh, one more thing. So when something is spinning, right, all parts of it spin at the same rate if it's rigid, right? Which is most things are rigid. In other words, they're held together, right? If I spin this thing, the edge of it doesn't rotate faster than the middle. It all spins at the same rate. However, if you put my finger further or closer to the point that it's spinning about, that changes the r, right? So what happens if r changes? Suppose r gets bigger. What happens to the v if omega is the same over? It gets bigger, right? So the further you put something from the center or from the point it's spinning about, the faster it's moving, right? The bigger the v. And the closer it is to the center, the smaller the v. So that's an important thing. So if I put my finger in the middle, right, it doesn't move. It just sits there, right, because the r is 0, right? But if I put it on the edge, then it spins, goes all the way around the edge. So that's something else to pay attention to. All right. So this is where it starts making more sense when we start doing this angular acceleration stuff and start putting some basic equations together. So if you remember what we did when we did 1D kinematics, once again, we start with average speed, well, distance displacement, but then average speed, velocity, and then acceleration. Remember we talked about acceleration after we talked about velocity. So if you go back to 1D kinematics, right? When is there acceleration? How do you get an acceleration? What has to happen?
Change in velocity.
Right, change in velocity, right? So associated with an angular velocity is an angular acceleration. So basically the same idea. If the angular velocity changes, then that creates an angular acceleration. that means if the thing spins faster or slower or changes direction, right, spins clockwise and then counterclockwise, then there's an angular acceleration, right, that isn't zero. So the average angular acceleration, by the way, is given by this alpha thing. It's a fish thing, right? It's a Greek symbol. It looks like a fish, but it's alpha. And that represents the angular acceleration, alpha. It's just defined to be, the average angular acceleration, sorry, is defined to be the change of omega, how fast, the difference between the initial angular velocity and the final angular velocity, right, divided by the time it takes to change from one to the other, right? It's the same thing as, almost the same thing as average acceleration. It was delta v over delta t. This is delta omega over delta t. So they're very similar. And then, let me say the units, sorry. I was skipping this point here. But the units of it is the units of omega, which is radians per second, divided by second. So you get radians per second squared, which is kind of like meters per second squared for the typical acceleration you're talking about. So we didn't really mention that much about average acceleration when we did it on test one. What we did is constant acceleration, right? So we said if the acceleration never changes, it's always the same thing, then you have a constant acceleration. The constant acceleration is equal to the average acceleration because it never changes. You do the same thing here. So the thing we're going to focus on for this stuff is constant angular accelerations, right? So basically if the amount of the angular acceleration and the direction, which I'll get to in a minute what the direction means, doesn't change, then it's a constant angular acceleration. And for that case, the average angular acceleration is equal to the value of its constant acceleration. That's what I wrote here. So if it's constant, then the value of its constant acceleration is equal to the average. But the average is equal to this, which is delta omega over delta t, which is omega f minus omega I over t. T is the time it takes to change from omega I to omega f, right? That gives you that tells you how to calculate the constant angular acceleration. But what you can do is you can solve this equation for omega f. When you do that, you get omega f is equal to omega I plus alpha t. So this tells you how fast something is spinning and in what direction it's spinning. If you know how fast it's initially spinning, what the angular acceleration is and what the time is. But what does that look like? So it's omega f is equal to omega I plus alpha t. So what does that thing look like? It looks like vf is equal to vi plus at. In fact, there are all these sort of analogies between what you did in 1D kinematics and rotational motion, especially when you're talking about constant angular acceleration. So it's very similar to what you did in test one in the end, not that different. So we'll go into this. There's a couple more equations that are like this, right, which we can talk about. But before I do that, let me just mention one more thing. If you take this definition of alpha, which is omega f minus omega I over t, and multiply both sides by r, you don't know why I'm doing it, but you will in a second. You get alpha r on the left, and then you're multiplying everything on the right-hand side by r. So I have to multiply omega f by r to omega I by r. That gives you this equation here, right, when you expand it out. But v is r times omega, right? So v is r omega. So this is r omega f. This is r omega I. That's vf and vi, right? So it's the initial velocity of this vector and then the final velocity of this vector if you change omega, right? So this thing is spinning slowly like this. You get a certain v, right? Then if you make it spin faster, you get a different v because it's r times omega, right? So this tells you r omega I is what this is initially. R omega f is what it is in the end, right? It's the final vf. So that's what this is, vf minus vi over t. But what is vf minus vi over t? It's the constant acceleration. It's what you did in test one. If you did vf minus vi over t, that gives you the constant acceleration, not angular acceleration, just acceleration. So what you get is that this thing is the acceleration, and that's equal to alpha times r. So this is sort of like your normal acceleration from test one. But in terms of the angular acceleration, it's alpha times r. What does this tell you? This gives you what's called your tangential acceleration. What does that mean? Like I said, if this thing's spinning slowly like this, right, then your v is some small thing, right, because it's spinning slow. If you make it go faster, this becomes bigger, right? So if you subtract those two things and divide it by the time it takes to change from one to the other, that gives you your acceleration of this velocity vector. which is the tangential acceleration, because it's a measure of how much your tangential velocity changes. And that's how you find it. It's just alpha times r. You just take your angular acceleration and you multiply it by r, which is the distance from the point that it's rotating about to where the point is, right? That gives you a measure of how much your velocity is changing over time. Okay. So there's 2 more slides I want to do, and then we'll do some examples, but let me just get through it. So like I said, there's all these analogs to stuff you did on test 1 for rotational motion. For instance, v kind of acts like omega, right? This is the equation that relates v and omega, right? This is the equation that relates the sort of typical acceleration to the angular acceleration. A is equal to r alpha. Then you have this thing where like d is equal to r delta theta. So you know, distances or displacements are kind of like delta thetas. So what you can do is take all the equations you learned on test 1, which most people did well on and most people sort of got, right? The 1D acceleration equations. And you can turn them into the constant angular acceleration equations. So what you do is you change all the delta x's to delta thetas. You change all the v's to omegas. You change all the a's to alphas. When you do that, you get these equations. You don't have to derive them. You can just come up with them through these analogs. So this equation becomes this equation. You're just changing delta x to delta theta, vi to omega I, a to alpha, right? And then similarly, you get all the rest of the equations, right? So these are the constant angular acceleration equations, which are on test 4. And you can use these to figure out how fast things are spinning after some time, how much angle they spun through after some time, how long it takes them to change from one omega to a different omega. It's the same kind of problems you did on test 1, except you're doing with rotational stuff. So, like I said, these things are vectors, though. I mean, delta theta, v, omega, delta theta, these are vectors, right? So basically, when you go counterclockwise, they're positive. When you go clockwise, they're negative by convention. And alpha also has is also a vector. So it has a sign too. But the sign is related to whatever the sign of omega is. Remember when we did 1D kinematics? The direction of A didn't matter unless you put it in the context of V. So if V and A are in the same direction, what happened from test 1? Like V and A are in the same direction. It speeds up, right? Remember? If V and A are in opposite directions, it slows down. Same thing here. So you have a direction for omega, right? Positive or negative, whether it's going counterclockwise or clockwise. You have a direction or a sign for alpha, right? It could be positive or negative too. But what I'm trying to say is if they both have the same sign, if they're both positive or both negative, it means that the thing spins faster, right? If they both have opposite signs, one's positive, one's negative, then the thing slows down. It's the same, sort of the same thing what you did in 1D kinematics. Okay, so let's do some examples with this. It's actually not too bad. All right, I'm going to turn this thing on. Okay. All right, let's do some rotational motion equations. All right. So it used to be a DVD when I first did these examples, but I've moved on to Blu-rays, right? All right, it is spun counterclockwise about its center. So when you stick a DVD or Blu-ray, whatever, into a Blu-ray player, it spins about its center, right? So this is sort of how it usually goes. From rest to an angular velocity of 20 radians per second. So I only mentioned 20 radians per second, but it is spinning counterclockwise. So there's two things mentioned, right? It's 20 radians per second counterclockwise. In a time of 1.2 seconds under a constant angular acceleration. Okay, so this is the given information. And the first thing we want to figure out is what is the angular acceleration. Okay, so what we're going to use is these equations I showed you on the PowerPoint, right? Which I'm going to write down here. One of these equations. It's kind of like what you did on test 1. You just pick the one that you need to use, right? The one that has the thing you're trying to find, and everything else is given. So this is one of them. It's omega f is equal to omega I plus alpha t, which is like Vf is equal to Vi plus AT. You had another one, which is Vf squared is equal to Vi squared plus 2a delta x. That becomes omega f squared is equal to omega I squared plus 2 alpha delta theta. You had this one, delta x is equal to VIT plus 1/2 AT squared. So that becomes delta theta is equal to omega IT plus 1/2 alpha t squared. And then there's a couple others, we don't use them that much, but another one, just as an example, was delta x is equal to 1/2 VI plus VF. It's kind of hard to say something, write something else, by the way. But it's the 1D equation on test 1 was 1/2 VI plus VF times T. So that becomes 1/2 omega I plus omega F times T. Okay, so there's another equation, but we hardly ever use it, right? So we're going to focus on these. Okay, so what, first of all, are we trying to find? Because it's not so obvious. I mean, when I asked for the acceleration, it was just the thing that was A, right? So these are Greek symbols. So the question is, which one of these Greek symbols are we even trying to find? Right, you're trying to find the fish thing, right? Which is alpha. That's the angular acceleration. Okay. So we're trying to find this thing. Right, I can't really draw. Okay, so the question is, what are we given? All right, let's go up here. Okay, so we're given the time, right? So we have to use that somehow. What else are we given? It starts from rest, right? So what does that mean if it starts from rest? Which one of these things is 0 if it starts from rest? Is it this thing? Is it this thing? Yeah, it's omega I, right? Omega I, this thing here, is 0. And then we know this, 20 radians per second. So the question is, what is the 20 radians per second thing? Yeah, it's omega F. So we know omega F, we know omega I, we're trying to find alpha, and we know T. So which equation do you think we use? Yeah, the very first one, right? Use this one. So it's just like what you did on test 1, right? Except you're just, finding different things than you found in test 1, but the procedure's the same. So this is 0 because it starts from rest. So omega F is technically positive 20. And the reason why it's positive, it's because it's counterclockwise, right? If it's clockwise, it would be negative. And then you divide that by 1.2 seconds, and that gives you your alpha, which is also positive, which I'll explain in a second. Sorry. I think this is 16.67. Yes. So it's 16.67. So the units are radians per second squared because, that's the units, but it's radians per second divided by seconds, which give you radians per second squared. Now it's positive, so omega is positive, alpha is positive. That means it's spinning faster because they both have the same sign, right? So, which is what it's doing. It's going from rest to making it going faster than rest, right? 20 radians per second. Okay. So that's the first thing that we found for the angular stuff. Now we know the angular acceleration. So the next question we can answer is, what angle does the blue ray spin through in 1.2 seconds? So, if you watch the thing spin for 1.2 seconds, and you watch a point of it go around, it goes around some angle, right? So that's what we're asking. How much angle does it go around in 1.2 seconds? Okay, so what are we even asking here? So which one of these symbols, right, are we trying to find for part B? What do you think? Well, it's not omega I, omega F, right? We used that in the last one. It's not alpha. We went over that. It's not T. It's the only thing that we haven't talked about yet, which is delta theta. So we're trying to find this delta theta thing. Okay, so you can use alpha, correct? Because if alpha is correct, you can use any of these equations. But suppose you get alpha wrong, and you don't want to get part B wrong. What is the best equation to use? I mean, it's obvious. It's the only one that doesn't have an alpha in it, right? Which is which one? This one. So this one's the best one to use just in case you have alpha wrong, right? And we can use it because we know omega F and omega I, we know T. So let's do that. So we're going to use, so this is just 0, and this is of course, this would be the, technically omega F has to be the omega at 1.2 seconds, which it is, right? It's given. So when you do that, you get delta theta. Oh, yeah, you can just do it. It's 10 times 1.2, which is just 12. So you get plus 12. So the delta thetas can be plus or minus 2. If it's plus 12, it means you go 12 radians counterclockwise, right? If it's negative 12, it's 12 radians clockwise. All right, so does that make sense? Now, it's radians because the seconds cancel out. It's not degrees. So, radians are sometimes a little bit weird to use. And you might want to convert to degrees, but the better thing to do is ask something like this. This comes up all the time when we do rotational stuff. The question is, how many revolutions does the Blu-ray make in 1.2 seconds? So this gives you a better sense of what's going on, right? Because if it's 2 revolutions, you know it goes around like 2 times. This is just a conversion, though. If you want to figure out how many revolutions, all you have to do is the first thing you have to do is figure out delta theta. And then this is a conversion from radians to revolutions. That's all it is. So what we want to do is we want to convert this answer that we got in part B from radians to revolutions. So how are we going to do that? Does anyone know? So how do you relate radians to revolutions? Or everybody think about it as what is 1 revolution in terms of radians?
Isn't 1 revolution 360?
Yeah, that's right. It's 360 degrees. But in terms of radians,
Oh, 2 radians.
almost
2 pi.
2 pi radians, right? It's 2 pi radians. So 1 revolution is 2 pi radians, right? That's the thing to remember. So you're just converting. It's just a conversion, right? So I want the radians at the bottom because I have to cancel it. So this is 2 pi radians at the bottom. And then there's one revolution at the top. So it's just a conversion. You just divide 12 by 2 pi, and that gives you your answer in revolutions. So it's almost 2 revolutions, not quite. It's 1.91. So it's gone around once and like 90% around the second time, but not quite, right? So this is what is common. It's not commonly asked, but we ask it quite often, right? How many revolutions does it make? So you have to do something like that to convert to revolutions. All right, does that make sense? Do you want to do the next example now or after the break? Actually, sorry, there's one more part here. There's one more part. Yeah, okay, we can do it after the break. If a piece of dust, so I use dust a lot in these examples. The reason why I use dust is because, first of all, dust sticks to everything. And second of all, dust doesn't weigh much, so it doesn't really affect how things rotate of the Blu-ray. So this is also pretty easy to answer, but it's relating omega to V. So let me just show you what sketch a picture of what's going on there. So this is the Blu-ray, And, you know, suppose, so it's spinning, right, at 20 radians per second at counterclockwise, right? This is the new sort of thing, notation, right? It's spinning at 20 radians per second. So if you put a piece of dust, this is a little piece of dust, and it's, you know, 0.05 meters, oops, from the center, right? So this is the center, right? And this is well, this little piece of dust is going around, of course, in a circle like this, right? So at this point, when it's at 20 radians per second, that's what I mean by at this point, this thing is going to be moving at some speed, right? Some velocity that's tangent to the path that it's going around, which is a circle, right? It's called the tangential velocity. So that's what we're trying to find, what that v is, right? So that v is given by a very simple equation, though. It's just given by this equation, right? If you know how fast it's spinning, you just multiply it by the distance from the thing that you're looking at to the point it's spinning about, and that's it. But something a little bit weird happens here with the units. Let me show you. This is 20 radians per second. It was given to be 20 radians per second. Okay. So that's 1. But the question is, what's the units? All right, see, meters times radians divided by second. It seems like it's a meter in radians per second, but of course this is a velocity. So what's velocity always measured in so far to this point? It's just meters per second. So the question you might ask is, what happens to the radians? Well, they sort of just magically disappear. It's something. It's convention in math, right? You also see it with circumference, right? We already went over circumference, right? What's circumference of a circle? It's 2 pi times 2 pi radians times the radius of the circle. But what do you measure? When you get done with your answer, what do you say? It's like in meters or in inches, right? You don't put radians in the circumference, right? In the end, the circumference is measured in inches or meters or whatever. There's no radians in there anymore. So yeah, it's this weird convention where the radians kind of just disappear and you're left with typical sort of units, right? That happens every once in a while. All right, so does that make sense? All right, so we'll do the other example after the break. You can take your break now. Okay, so what we're going to do is another example using the same thing that we just did here, but for a different example. So let's do that. Okay, so a circular tire. Okay, so tires are circular, basically. With a radius of 0.25 meters, is rotating counterclockwise about its center. Yeah, this is something new, which I'll explain when we do the calculation. At 200 revolutions per minute, it's another way to describe how fast things rotate, or spin, I should say, which is also called RPM, right? Which you probably see at some point or other, right? And so the angular acceleration is given this time, I don't have to find it. So the angular acceleration is constant, and its value is -3 radians per second squared. All right, before you even ask anything, it's spinning counterclockwise, and the angular acceleration is negative. So counterclockwise is positive, and the acceleration is negative. So does that mean that the tire is spinning faster over time or spinning slower over time? Slower. It's going to spin slower over time. So the first thing I'm going to ask is something related to this. How long? What? I just changed my font size. How did I do that? How did I do that? Does anyone know the shortcut for doing that? Is it Control Z?
No, but that'll undo what you just
There it is. It's value. Yeah, it is to undo. That's good to know. Okay, so the question is, how long does it take to stop spinning? I don't know how I changed the font size on the fly, though. I've never done that before. Okay, so what we're going to do is use the same equations that we used for example, the first example to figure out the second example. So I'm just going to copy those equations down quick, and then, we'll use them. So it's the same equations, right? These equations will be on your equation sheet all the way on test 4. Okay, so what do we know? We know alpha, right? The angular acceleration, that's given. We know a couple other things. For instance, it stops spinning, right? So what do we know? What does that tell you if it stops spinning? Right, omega f is 0. We know how fast it's initially spinning, although it's in some weird way of saying it, but we technically know omega I, right? So what equation do you think we use to find t? Yeah, the first one again, right? This stuff isn't too bad, I don't think. All right, so we're going to use this one. Omega f is 0 because it stops spinning. So then you solve for alpha somehow. So you could subtract omega I from both sides. And yeah, minus omega over alpha. I'm just trying to run alpha. For some reason I can't write them all down. Okay. So what we need to do, though, is figure out what omega I is in radians per second. We want to use radians per second squared for everything, radians for the angle. So we need to convert, it's another conversion. We need to convert rotations or revolutions per minute to radians per second. Yeah, that's what I wrote here. We need to convert RPM to radians per second. So it's just another conversion. So let's think about how we're going to do this. So omega I but that's the same thing as a revolution per minute. So what we need to do, I'm going to make this one long thing, is we need to convert, actually, no, I'm not going to do that, sorry. We need to convert revolutions to radians, like we did already. And we also have to convert minutes to seconds, obviously, right? Because we want it in radians per second. So I have to multiply this thing by 2 ones, basically. One to convert revolutions to radians, and then one to convert minutes to seconds. So how do we do this? So one revolution, what's one revolution again? Right, it's 2 pi radians. So the revolutions have to be in the bottom to cancel the revolutions at top. And then we have to convert minutes to seconds, which is easy. How many seconds are in a minute? 60, right? 60 seconds. Oh, sorry, other way around. 1 minute and then 60 seconds, right? Because you don't have to convert, cancel out the minute, right? So in the end, you get omega I is positive 200. Then you have 2 pi and a 60 here. And then you have radians per second, right? Radians per second. So that becomes 20.93. So that's the omega I. So so you're just plugging it into what we have here, like this thing here. But of course it has to be in radians per second, so you get negative plus divided by alpha, which was minus 3. And that tells you how long it took. It's almost 7 seconds, because if it was 21 radians per second, it would be exactly 7, but it's not quite. It's a little bit less than that. So it's like 6.98 seconds, right? That's the time it takes for the tire to stop spinning. All right, so does that make sense? Okay, part B is what's the tangential velocity? This comes up, and the next thing we're talking about, the next major topic we'll be talking about, actually starting next week, which is rotational kinetic energy of things moving, actually total kinetic energy of things moving. So this kind of thing comes up when we talk about that stuff, of the tire at 4 seconds. Okay, so we're trying to figure out how fast the edge of the tire is moving, right, basically, at 4 seconds. So that's what we did in the last part of the last example that we did before the break. It's just using this equation here, right? V is equal to R omega. I can't write anything today. Nothing is coming up. Okay, so the V is the thing we're trying to find. R is the distance from the edge of the tire to the point it's spinning about, which is the center, which is just the radius of the tire, right? And omega is how fast it's spinning, but for this case, it's how fast it's spinning at 4 seconds, right? So we don't know how fast it's spinning at 4 seconds. We know that it's initially spinning at 20.93 radians per second. We know that after almost 7 seconds, it stopped. But the question is, how fast is it spinning at 4 seconds? We have to figure this out. So that's the next thing we need to do. We need to determine how fast it's spinning at 4 seconds. Okay, so what equation do you think we're going to use if we want to answer this question, how fast it's spinning at 4 seconds? So which one of these equations is the best one to use if we want to figure out how fast the thing is spinning at 4 seconds? If we know the time is 4 seconds, we know alpha, and we also know what it starts out with, which is omega I. So which is the best one to use? Again, 1. Yeah, we used this one 3 times, I think, already. It's a common one. So this is 20.93 because we found that out in the last part when you convert it to radians per second. The alpha was given, and the time is obviously 4 seconds. You can almost calculate this in your head because 4 times negative 3 is minus 12. So it's 20.93 minus 12, which is 8.93, positive. So it's spinning counterclockwise, right, at 8.93 radians per second. Okay, so then you just plug it in here, right? This is why we did that. So you could say this is like VF maybe. You don't have to even label it, but so it's a little bit less confusing. I label it as VF. But the radius of the tire is 0.25 meters. That was given at the start. And so it's just basically a quarter of 8.93, which is 2.25. So that's how fast the edge of the tire is moving after 4 seconds, right? 2.25. All right, the last part of this one, I think it's the last part of this particular problem, yes, it's a simple thing to calculate, but to conceptualize what we're calculating here is an important thing. That's why I asked it. What's the tangential acceleration of the edge of the tire? You might think, don't we need to know a time or something? No, because it's a simple equation to find the tangential acceleration. It's just the angular acceleration times r. That's it. It doesn't depend on time because the angular acceleration is constant. It means the tangential acceleration is also constant. It's the same value for all times. So this is easy to figure out because we know all these things. This is alpha, and r was 0.25. So it's just, this is also something you can calculate in your head. Once again, the radians kind of disappears again when you do this, and you just get typical units. It's negative 0.75 meters per second squared. The reason why I asked this, besides to calculate it once, is it gives you a sense of what's going on when you calculate these tangential and both velocities and accelerations. So here's your tire, right? And at 4 seconds, Oh, sorry. So, for this case, we know how fast it's spinning at 4 seconds. It was like 8.93 or whatever. But it's spinning counterclockwise at this, 8.93, whatever it was, radians per second. And the edge of the disk, if you look at the edge of the disk, just the bottom part of it, it's moving at that time of 4 seconds, like this. It's moving in that direction, right? The edge of it. It's 2.25 meters per second, right? But it's changing because omega is changing, right? It's getting, the tire's slowing down, spinning. The rate that it's spinning is slowing down, which means the V is slowing down, right? For the V to get smaller, you need an acceleration in the opposite direction, right? As I explained in the PowerPoint, but here's another example of it. So the acceleration is negative, right? That's what we just found. So this is the acceleration. It's negative, sort of in the negative direction. So they're opposite directions, right? The tangential acceleration and the tangential velocity are opposite directions, which means the velocity is going to get smaller over time. And that's true because omega is getting smaller over time, right? So the V is going to get smaller over time. All right, so does that make sense? What that is, what we just found? Okay, so I want to do one more main topic today and do one more example with it, and then we'll do the rest next week of this PowerPoint. So the next thing I want to talk about is rotational kinetic energy, and this thing called moment of inertia. So suppose you have a disk that's spinning, like this DVD. It's just spinning around, right, like this, and you stick a bunch of little masses on it. They're called point masses. Now, what I mean by point masses is they're very tiny in size, right? They could have mass. They could be dense, and they could have mass that isn't small, but size-wise they're small, right? So they're called point masses. And you stick them at random points on the thing that's spinning. So I put one here, one here, one here, one here. And if you know how fast it's spinning, you can figure out how fast each one of those things are moving. It's what we just did in the last sort of example, right? Like how fast the edge of the tire is moving. It's the same idea, right? So this thing's spinning like this, then this mass is moving at some speed, this mass is moving at some speed, this mass is moving at some speed, and that mass is moving at some speed. But how fast are they moving? You can figure it out. It's just how far they are from the axis times how fast the disk is spinning, right? That gives you how fast they're moving. And then what you can do is figure out how much kinetic energy does each one of these things have, right? So kinetic energy is, of course, on test 3, just normal sort of kinetic energy. So how do you figure out kinetic energy? What's the equation for it? Right. So what's the kinetic energy of mass 1? It's 1/2 m1 v1 squared, right? What's the kinetic energy of mass 2? It's 1/2 m2 v2 squared. So on and so forth, right? So if you add them all up, this gives you the total kinetic energy of all these point masses, but we call it the rotational kinetic energy because they're all spinning around, right? They're not just moving forward, they're all spinning around, right? So that's where rotational kinetic energy comes from. It's just the sum of all the kinetic energies of all those point masses spinning around. However, like I said, the kinetic energy of this one is 1/2 m1 v1 squared, right? Everyone gets that? But v1, like I said, is r1 times omega. r1 is the distance from this mass to the point it's spinning around, right? So instead of writing it down as 1/2 m1 v1 squared, you can write it as 1/2 m1 and then r1 times omega squared, right? Instead of v, you write r omega squared, right? r1 omega squared. The kinetic energy of this one would be 1/2 m2 r2 times omega squared, right? So that's what I did here. I wrote these things in here. This is r, instead of writing v, I wrote r1 omega squared. Instead of writing v2, I wrote r2 omega squared. But the omega is the same for all of them, right? Because they're all spinning at the same rate. The r's could be different, but they're all spinning at the same rate. So what you can do is after you square both terms in there, so you have an r1 squared omega squared, r2 squared omega squared, whatever, you can pull out the omega squared because it's common to every single term. You can also pull out the 1/2 because it's common to every single term. And what you get is 1/2 m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared times omega squared. And the thing in the middle is called the moment of inertia. That's the new thing here, right? So I'll explain that in a minute. But before I explain it, if you call this thing the moment of inertia I, and you stick it back into this equation here, you get 1/2 I omega squared, right? Which is the rotational kinetic energy that something has, is 1/2 I omega squared. Now there's all these analogies between stuff you've already learned and this stuff. So once again, we already said it 2-3 times. So just one more time. What is the kinetic energy normally? Like typical kinetic energy for test 3? What 1/2 mv squared. So omega is the analog of v, right? And you have this equation here, which is 1/2 I omega squared, right? That really is similar to 1/2 mv squared, right? So omega is the analog of v. What do you think is the analog of mass for rotation? I, this thing called moment of inertia. So what does it mean to, just from a common sense point of view, right? If you have something that's more massive than something else, what does that mean? It means it takes more force to get it to move. It takes more force to get it to stop or change direction, right? It's the same thing here. The bigger your moment of inertia, the harder it is to get something to rotate. The harder it is to get something to stop rotating, right? It's the same thing as mass for things that rotate, right? That's what moment of inertia is. And this is what it is for point masses. So it's on this slide here. This is easier to see, right? That's for a bunch of point masses rotating about some point. That's the moment of inertia. Now, the weird thing is, not the weird thing, but you have to think about it a little bit, is how can you change the moment of inertia? Well, one thing you can do, let me go back to here. One thing you can do is you can change all the masses, right? If you make them all, say, bigger, right? Say all those masses become bigger. What happens to the moment of inertia? It becomes bigger, but that doesn't really, that's not surprising. I mean, if you put more mass on something, it's probably harder to turn. But what else can you do? So it depends on the m and the r, right? So suppose I take all these masses. I don't change the mass, right? But I just move them so they're closer towards the point it's spinning about. What happens to all the r's for that case? Yeah, all the r's go down, and the moment of inertia gets smaller, meaning it's easier to spin those things if they're closer to the point it's spinning about. The other thing I can do is move them further away. And obviously the converse is true. If you move them further away, if you have the mass further out from the center, it increases the moment of inertia. It makes it harder to spin, right? So this is something you can use. More concentrated mass, easier to spin. Further away, it's harder to spin, right? The other thing you can do that's not so intuitive is you can change the r without changing where the masses are. Does anyone see a way to do that? So if I keep all the masses in the same spot, the same mass in the same spots, does anyone see a way you can change the r's?
You increase the surface.
No. So you're not, it's a little bit hard to think of. I'm just seeing if anyone can think of it before I tell you. You're not changing anything here. The size of the disk does not change. Where the masses are don't change, and the masses themselves don't change. So does anyone see a way you can change the moment of inertia? What was that? Yeah, I think you're close. So these r's are the distance from the mass to the point it's rotating about. So one thing you can do is change the place where it's rotating, right? So most things rotate about the center, but that's not necessarily true. So I could take this DVD and put my finger here, and sure, it rotates about the center. But I can put my finger here. Instead of rotating about the center, I can make it rotate about my finger over here. So it's not rotating about the center. It's rotating about like a point over here somewhere, right? Like where my finger is, right? Which is like here. So if I do that, all the r's change, right? The distance to that point changes, right? So it depends on the axis it's rotating about, the point it's rotating about. It also depends on where the masses are and the amount of the masses. All three things can change the moment of inertia, which is more counterintuitive than just the mass, right? Okay, so the last thing we're going to do today is just a simple example with moment of inertia, and we'll do the rest next week. This stuff isn't too bad, as you'll see. Okay. Actually, we're going to do 3/4 of a problem. There's one part that we'll do on Tuesday, because I didn't finish in the other class. But we'll do most of it today. All right, so moment of inertia example. Okay, so I'm just listing these out because I'm going to copy and paste one of these sentences because the rest of them were pretty similar to the first. Okay, so you take a little point mass, or you can just think of it as a tiny little mass. It happens to be 2 kilograms, which is kind of massive for something small, but nonetheless, that's what it is. So you put one of them at x equals plus 2 meters, y equals 0 meters. And then you take another point mass. This is why I wrote it like this. And this one's 5 kilograms. And you put it at x equals 0, y equals plus 2. So that's the second one. And then you have the third one, which is also 2, but it's placed at x equals minus 2, y equals 0, right? So you have these 3 little tiny masses that are placed at random points on the xy axis. So, you know, I could either just, I could tell you where they are, I could just give you a sketch and show you where they are, or you could do both. I can tell you where they are, and you can make a sketch of where they are. So let's make a sketch of where they are. It makes it easier to understand what's going on here. All right, so these are tiny little masses, so you draw them as tiny little dots. So one of them is here. This is mass 1. And it's 2 kilograms. Other one's over here, which I'll call M2, and that's 5 kilograms. And you have another one, which is on the negative x-axis, which is the third mass, which is over here. Call this M3, and that's also 2 kilograms. And obviously, they're all 2 meters away from the origin. So you could label them all as 2 meters, but there's a reason why I'm doing this, and you'll see why actually on Tuesday. That's the part that we're skipping, sorry, today. But I'm going to label them as like all D, right? They're all equidistant, right? 2 meters. But I'm just calling it D, and obviously D is 2 meters, right? You'll see why I did this thing on Tuesday. All right, so does that make sense? You know, sketch makes sense at least? Okay, so the first part is, so I have to explain something in this sentence. But let me just finish writing the sentence, and then I'll explain it. Are rotating about the origin, which is x equals y equals 0, which is the z-axis. This is the part I have to explain. But let me just write what I'm writing here, and then I'll explain it. So, you know, as is the case for a lot of things in this class, we're making this stuff a little bit easier than it actually should be, but it's fine for this class. It's good enough. When something rotates about a point, right? Like, say something's rotating about the middle, like this DVD, right? Suppose it's rotating about my finger, which is the middle, right? It's actually rotating about an axis, right? So this axis is, you can think of it as the z-axis. It goes basically from the floor to the ceiling. It's this like line that goes from the floor to the, and it's rotating about the line, right? So it's not just a point. It's a point, it looks like a point in the 2D plane because as the line goes through the plane, it's just a point. But it's actually an entire axis. It's like a line. So what I'm saying is the z-axis can be anything. I could say that over here's the z-axis, right? Or over here's the z-axis, right? Or I could say, you know, the origin is the z-axis where the axis goes through. It goes through at the origin, right? So that's what I'm saying the z-axis is, right? So it goes through at the origin. And this is the notation or the way we'll do it all the time. The z-axis is going to be the origin, right? So it's rotating about the origin, right? That's what we're saying. And that's the z-axis. It's not that hard to understand once. And then once you understand it once, it's fine. So what does it mean? It means it's rotating, like here's the origin, this is the point it's rotating about, but it's, all these things are kind of rotating like this about, actually I have this piece of paper, this is like this piece of paper, right? So you have this piece of paper, and if I hold it in the middle, it's just rotating, all of them are rotating about my finger like that, right? Okay, so the question is, what is the moment of inertia about the z-axis? Because the moment of inertia depends not only on the masses and where they are, but what axis or what point they're rotating about, right? That's what we're saying here. So in general, the moment of inertia for a bunch of point masses is m1 r1 squared plus m2 r2 squared plus m3. Right, that's just the equation for moment of inertia. But I'm going to put this like a z here because you can talk about different axes, right? So this is moment of inertia about the z-axis. So all I got to do is figure out how far, how far are they to the z-axis, right? So how far are they all to the z-axis? 2 meters, right? That's it. It's pretty straightforward. So this is 2 kilograms times 2 meters squared, which is 8. 4 times 2 is 8, plus 5 kilograms times 2 meters squared, which is 20. So it's 28. And then the same thing again, right? Because mass 3 is the same as mass 1. It's the same distance. So it's 8 plus 8 plus 20, which is 36. So the moment of inertia about the z-axis is 36. All right, then you might say, what are the units? It has no special units. It's just units that are here. It's kilograms times meters squared because you're squaring the meters. Right? So that's the units, right? Kilogram meters squared. That's it. That's the moment of inertia about the z-axis, right? Not too hard, I don't think. All right, I'm going to cheat and copy this because I'm going to ask a very similar question, but obviously different, but similar to this. So I'm going to borrow a lot of the words from this one. All right, the next part, which is part B. So if all the masses are rotating about the x-axis, what is the moment of inertia about the x-axis? Okay, so what does that mean? I'll show you with the paper too. Well, it's not rotating, first of all, it's not rotating like this anymore. What I mean is, they're all spinning about the x-axis, so it looks like this. It's a little bit hard to draw, but they're rotating like this. Right? So instead of turning my paper like this, right? This is the x-axis, like left to right, so I spin it like this, right? So that's a different axis than before. So if you want to figure out the moment of inertia about the x-axis, it's the same equation, except that these r's are the distance to the x-axis, right? That's where you're trying to find the distance to the x-axis. So what is the distance from mass 1 to the x-axis? Right. What is the distance from mass 3 to the x-axis? 0. So the ones on the x-axis do not contribute to the moment of inertia about the x-axis. So the only thing you're left with is the one on the y-axis, and you might say, well, how do I find the distance to the y-axis? So let me show you something. It is 2, but you're just finding like the shortest distance to the y-axis. In other words, if you're trying to find the distance from mass 2 to the y-axis, right, you wouldn't do something like this, right? That doesn't really make a whole lot of sense. Or like this, right? It's just the straight distance from the mass to the, shortest distance to the axis, which is 2 meters again, right? Still 2 meters, right? So it's just 20, right? So that's the moment of inertia about the x-axis, right? It's 20. So the two so far, what do you think? Is it easier to spin about the x-axis or the z-axis so far, do you think? The x-axis, right? Because there's a lower moment of inertia, right? All right, the last one we're going to do for today, and then we'll do one more part with this on Tuesday, The same sort of question, but you can also do the y-axis. In fact, there's an infinite amount of axes you can do, but we're only going to do the x, y, and z axes. So the question is, what is the moment of inertia about the y-axis? Okay, so if you're spinning, if you want to figure out the moment of inertia about the y-axis, then you can picture them spinning about the y-axis, right? So you have this piece of paper. If the y-axis is like towards you, then you flip the thing like this, right? It's spinning like that, and that's a different way to spin it. So it's going to have a different moment of inertia. So it's the same equation, right? All the time. It's just that the r's are different, right? The r is the distance from the mass to the y-axis for this case. So what's the distance from mass 2 to the y-axis? 0. Once again, the masses on the y-axis don't contribute to the mass to the moment of inertia about the y-axis. So this one's 0 this time. All right, but what's the distance from the other two masses to the y-axis? It's the same thing, right? You just, once again, you don't do this, right? It's just that, right? That's the distance, which is just 2 meters, and the same thing for the other one, right? For this one, it's not that, it's that, right? So they're both 2 meters. So it's just 2 kilograms, right? Because that's mass 1. It's 2 kilograms. And then plus mass 3, which is also 2 kilograms. So this is the moment of inertia about the y-axis, which is 16. So out of all 3, which is easiest to spin them around? The y-axis, right? And then the x-axis and the z-axis, right? So that's not too bad, right? Okay, so then on Tuesday we'll do rotational kinetic energy related to this, and then we'll do some other things on Tuesday.